Navigating the harsh desert of technical execution is a brutal and unforgiving process, where your ideas, understanding and analysis are tested by the uncompromising laws of physics. At times, it feels like the process will never end. And then one day you wake up and you've got 50% of the first British-built all-new turboshaft engine in 40 years working on the test bench. Welcome back to PC1, and tonight we'll start by showing you the first 50% of GT50 running on the test bench. Manufacturing of GT50's compressor, combustor, turbine, fuel spray nozzles, gears, bearings and casings. Live testing of the GT50's starter gen, power management unit, fuel spray nozzles and engine drivetrain. We'll show you how we're manufacturing HX50's composite rotor blades. We'll introduce our completed all-new retractable wheeled undercarriage and an updated version of our attractive skids. And we'll give you an update on the testing of HX50's electrical system and class-leading digital cockpit. What started as a dream is now solid hardware. Let me show you what we've been building for you. The GT50 engine comprises 4 modules: the starter generator, the gas generator, the power turbine and the engine drivetrain, with 50% of those now operational on the test bench at PC1. Let's go and have a look at what we've been building for you. This is the very first prototype GT50 starter generator module, and it's central to both the aircraft and the engine's electrical system. Since developing it here on the test bench, it's run throughout its operating speed range and has now demonstrated the ability to generate enough torque to be able to start the very first GT50 engine. Its delivery combines high-speed machine design, precision manufacturing, advanced control system, sensing, instrumentation and software development, and then implementing those things on robust electronics capable of operating within the harsh electromagnetic interference environments found in high-frequency, high-voltage electronic systems. Testing of the starter generator has led to optimized control algorithms, optimized instrumentation configurations, to allow the system to operate effectively across its operating speed range. We've developed improved rotor balancing through an enhanced rotor design, bearing arrangements and a number of fairly significant mechanical design updates. The original manufacturing process involved disassembly of the starter generator rotor post-balancing to allow remagnetization of the permanent magnets. This was inadequate given that it's necessary to balance this rotating assembly so that its CG displacement from the axis of rotation is less than 1 micron. The moment you assemble and reassemble any mechanical system like this, it becomes impossible to hit those tolerances. So future production units will involve tooling that will allow the remagnetization of the rotor as an assembly, preventing that problem. Modern aircraft like the HX50 face increasing electrical and electronic complexity to meet the demands for a connected and automated flying experience. This increases the challenge of ensuring robustness against electromagnetic interference and high-intensity radiated fields. The starter gen you see here is the 5th iteration of the system, including subtle but important improvements throughout. Key enhancements include an improved rotor and bearing arrangement, tighter tolerances throughout, better alignment and balance, and a revamped manufacturing process that allows us to remagnetize the rotor as an assembly, ensuring smooth, vibration-free operation. These changes, though minor to the untrained eye, are vital for reliable performance and meeting the intended TBO. As with all of these things, the devil's in the detail, and the development process involves painstakingly chasing through all of the little details that really make these things work, many of which can only be identified through building and testing prototype hardware like this. Our team's strength lies in its ability to rapidly build, test and refine components because we have everything under one roof, achieving in days what would take larger organizations months to accomplish due to supply chain and vendor complexities. GT50 Module 1 is now ready to start the engine for the very first time. Module 4 of the GT50 engine, the engine drivetrain, includes critical components like the speed reduction gearbox, the drive shafts themselves, the Sprag clutch, torque and speed sensing instruments, the rear engine mounts, and most of the engine lubrication system. Beyond being a core engine part, it showcases years of advanced design and process development, including the design, release and production control processes, the development of thin-walled structural castings, aerospace-grade gear and bearing production, high-speed drive shaft production, sensor and instrumentation production, and test rig development. But this module represents a further significant milestone, being the prototype of the second major module of the first new UK designed and built helicopter gas turbine engine in the last 40 years. To manufacture the engine drivetrain, we've had to develop specialized capabilities to manufacture thin-walled structural casings from aerospace aluminium alloys. This involves advanced casting techniques for complex parts with varying wall thicknesses and intricate internal lubrication passages requiring ceramic core production and then removal post-casting, precise heat treatment and stress relieving processes to minimize the residual stresses. We've had to develop controlled fixturing and machining processes to prevent distortion alongside intelligent measurement, inspection and robust surface protection processes. Achieving the target wall thicknesses of 1.5 millimeters to hit the weight for these components poses significant casting and machining challenges due to the distortion and residual stresses that are inherent in these kinds of components. To accelerate the development of the machining processes, we've made selective use of advanced 3D metal printing processes as an analog to the cast production units. Multiple design iterations have been tested to balance the weight reduction with manufacturability, and the first prototype casings that bring all of these technologies together are currently on the test bench being tested. Over the last few years, we've developed the capability to manufacture high-quality aerospace gears. This painstaking process includes 30 stages for a typical helicopter transmission gear. Building the first speed reduction gearbox gear train required all elements of these processes to be brought together for the first time to deliver gears capable of passing the demanding endurance tests. The challenge is to make a gearbox that's sufficiently light while the loads on individual gear teeth are sufficiently low that each tooth maintains an infinite fatigue life. To do this, we use extremely high-grade double or triple melted super clean material. We require extremely tight machining and grinding tolerances. We deliver exacting heat treatment cycles to give precisely the right core and surface hardness in the gear material. And we carefully shot peen the root fillet to protect the root fillet from cyclic stresses and crack formation. We develop all of the necessary plating, inspection and protection and testing processes, but given that every application is different, it's been necessary to test and iterate each stage of the production process to reach the required performance and quality. And the very first cost-effective, world-class aerospace gears designed and manufactured by Hill are now running on the test bench. Hill Helicopters has now built conforming aerospace grade bearings right here at PC1 using the finest grade aerospace materials that money can buy on the highest quality machines that are available to do the task. We've done it at the price we said we were going to, and these bearings are now running right here on the test bench in the high-speed laboratory. What some people first thought was madness in delivering our vision for a lower cost general aviation is now right here in front of us and operating on the test bench. The GT50 engine architecture provides a rear power takeoff combined with a series of 3 concentric shafts to provide main rotor drive input, direct torque and engine speed measurement, and tail rotor drive input. The shafts are machined from solid bar down to thin-walled hollow tube with integral mechanical and drive features, with the blank being machined prior to heat treatment. Heat treatment generally results in distortion to the parts, particularly long, thin-walled parts, and therefore it's been necessary to develop elaborate machining and fixturing methods to minimize these effects. It's a real pain to keep these things straight. Given the high speeds at which these shafts rotate, we've also had to develop the processes necessary to robustly balance these shafts to ensure that the overall drivetrain runs smoothly and is free from vibration. The very first set of prototype Hill manufactured thin-walled drive shafts are currently balanced to specification, installed in the drivetrain, and are undergoing preliminary testing on the GT50 drivetrain test rig. This is the completed engine drivetrain test rig, and this is the very first prototype GT50 engine drivetrain. GT50's Module 4, the engine drivetrain, consists of the speed reduction gearbox that reduces the power turbine output from 36,350 RPM down to a more usable 6,004 RPM as an input to the main rotor and tail rotor drivetrain, and it's rated at 500 horsepower. It includes the main and tail rotor drive shafts, the freewheel unit, the N2 speed and torque measurement system, temperature, pressure and chip detection instrumentation, and the bulk of the engine lubrication system, as well as the rear engine mounts that attach the engine to the aircraft. The production of the engine drivetrain prototype and its test rig mark another key milestone in the GT50 program, demonstrating the company's ability to design, manufacture and test sophisticated gas turbine drivetrains. Within this prototype drivetrain are the very first Hill high-speed bearings, the very first Hill precision gears, the very first Hill drivetrains, the very first Hill thin-walled aluminium casings, and a plethora of other crucial aerospace components. All working and all built to the price point that GA needs. To validate the GT50 drivetrain prototype, we developed a specialized test rig to confirm the functionality, performance and endurance of each of the drivetrain components under the most demanding conditions. This is the fully commissioned and operational GT50 drivetrain test rig. The test rig uses two GT50 drivetrains working antagonistically in a closed loop, allowing precise control of torque and operating speed to test the function, performance and durability of the drivetrain units. Static torque is applied to keep the dynamic components fully loaded, with the rig consuming minimal power to overcome the frictional losses and drive the ancillaries like the pumps and heat exchangers. The test rig is also fully instrumented to measure speed, torque, lubricant pressure, lubricant temperature and flow rate, and a whole host of other monitoring parameters to support the development. The rig also features independent lubrication pumps to test and optimize the drivetrain's lubrication system to enable the on-engine pumps to be configured for minimum power consumption and weight. With the test rig commissioned, we've now started the engineering testing of the GT50 drivetrain system. First, we commissioned the test equipment, control system and instrumentation to ensure it operated correctly. The first system test was the engine lubrication system to ensure that the system supplied adequate oil to the gears and bearings to prevent wear and manage heat buildup. This initial testing involved a visual inspection of all of the jets within the gearbox to ensure they were all functioning correctly, followed by the calibration of the pressure and scavenge pumps and the heat exchanger performance to balance the flow of lubricant throughout the system. With the lubrication system validated and calibrated, the full drivetrain was assembled and the basic functional testing of the gearbox has commenced, including basic operation of all of the mechanical systems and sensors, all of the data acquisition, and all of the other instrumentation on the rig. The tests are currently ongoing and will extend all the way through the speed and the torque range required by normal operation. While the basic function of the gearbox is being tested, detailed data will be gathered to ensure that the casings, the gears and the bearings are all kept within acceptable temperature ranges and that the cooling system is able to cope under all operational conditions. During all of the performance and functional testing, careful attention will be paid to the noise of the system to ensure quiet running. Balancing and vibration is an important issue for all rotating machinery, particularly those operating at high speeds. The functional testing of the gearbox will ensure that the system's free from harmful vibration throughout the operating range. A key part of functional testing to be carried out on the gearbox is the so-called contact patch development testing, in which the build and setup of each gear pair is carefully assessed to ensure that the rolling action from one tooth against another is correctly delivered. This is crucial for the efficiency and durability of the gearbox, and achieving the correct contact patch can only be delivered if the gears and the related components are accurately manufactured and properly assembled. Once all the functional testing is complete and the drivetrain is correctly set up, the first of the engineering endurance tests can then be carried out to validate the life and the endurance of the system under load. One key area the team has been developing is the GT50 engine's rotor and stationary component designs to ensure that in the rare event of a turbine blade failure, the blade is contained within the engine's casing to prevent a hazardous effect on the aircraft. The design optimizes the failure sequence so that the blade fails at the root rather than the heavier blade cob or disc, which are harder to contain. While final verification will come from blade-off testing, the detailed simulations of the gas generator turbine and the power turbine under overspeed burst conditions show promising containment capabilities for the gas generator casing, with minor modifications likely to be needed for the power turbine's casing. These updates are being incorporated before the engine's first test run. These advanced simulation methods provide our engineers with unprecedented insights into the engine's behaviour under extreme conditions, a capability not available just a few years ago. With most engine design issues resolved, the focus has shifted now to rapidly producing the components for the GT50 core modules. The latest increased efficiency, increased flow capacity impeller is now in production. The blanks have been machined from high-grade aerospace titanium and subjected to rigorous heat treatment to deliver the exacting material properties required for its demanding duty. Extensive machining optimization trials have been carried out to optimize the balance between high-speed machining, given the lowest cycle time, versus the cost of the tooling consumed in doing it. These processes initially were developed on the lathe and the 5-axis and have now been implemented on the new Multus machine, allowing the compressor to be machined from a single heat-treated billet to finished component without ever leaving the machining center. The GT50 combustor's aerodynamic and thermomechanical designs are now stable, enabling the production team to focus on the development and manufacturing of tooling for roll forming, expanding and pressing the components. The combustor is primarily made from high-performance nickel-based superalloy strips, which are rolled and welded into rings, roll-formed into profiles and expanded to size, and then supplemented with rear-end pressed or cast components. The assembly is laser welded, incorporating the gas generator nozzle guide vane and fuel nozzle interfaces, and then laser or CNC drilled for cooling and dilution holes. While tooling production is labour intensive, it does enable low cost, high volume unit production. The prototype combustor includes an improved pressed rear face and floating washer to accommodate the axial and radial movements between the combustor lining and the combustor casing. The fuel spray nozzles for the GT50 gas turbine engine have been developed to ensure reliable ignition at all altitudes, efficient combustion and low emissions through effective fuel atomization across the operating range. To achieve the required 10:1 turn-down ratio without excessive fuel system pressure, the dual orifice nozzle is used, for which in a small engine with an annular combustor leads to incredibly small components. This is the fuel nozzle manifold, and this essentially penetrates through the combustion casing and positions each of the 12 fuel nozzles inside the rear face of the combustion liner. Within each of these fuel manifolds, the tiny fuel spray nozzles, which are assembled from 4 of these tiny components, are then assembled and mounted into each of these nozzles. Due to the limited public data available on suitable swirler and atomizer designs for engines with fuel flow rates at our level, it was necessary to use an experimental program to determine the exact geometry required to create the flow properties we needed from each of the nozzles. This involved reviewing all publicly available data on liquid spray nozzles, designing a range of geometries to meet the mass flow, cone angle, and mean Sauter diameter requirements. The team then procured and commissioned the manufacturing equipment that you can see behind me, trained the staff, produced the initial nozzle components, and validated the geometry with detailed inspections of surface finish and all of the crucial geometric dimensions. We developed a test plan to evaluate fuel spray nozzle performance and characterize them to enable the design of the fuel system diverter valve that controls the flow between the primary and secondary nozzle orifices. A specialized test rig has been designed and built to measure the mass flow, cone angle, and mean Sauter diameter of candidate nozzle geometries, supporting both experimental development and production nozzle testing before they go into engines. The rig controls pressure differential across the nozzle orifice and then uses an electronic proportional flow valve to measure the resulting mass flow, while laser visualization methods assess the cone angle and the droplet size. The rig features an 8x rated axial blower for ventilation and a fuel air separator to prevent the contamination and hazardous atmosphere development within the visualization chamber. The rig will be fully operational within 1 to 2 weeks, with the first Hill dual orifice nozzle components being completed next week, literally just as soon as the last form tool arrives. The GT50's first stage nozzle guide vane is a single piece component cast from nickel-based superalloy, featuring integral cooling channels to enhance the durability and lifespan of the unit. In production, these cooling channels will be formed using ceramic cores during the casting process, but to avoid premature investment in the core leaching equipment, prototype NGVs are cast solid with cooling channels created via EDM, using the equipment behind me and the tools that you can see here. Over recent months, casting processes were developed to produce the NGVs as a single ring, with shrinkage and accuracy qualified and then corrected. The tooling for forming the cooling passages and the EDM processes have now also been developed and produced in-house. Initial EDM trials on early scrap castings have validated the process, and the shrinkage corrected castings are now being manufactured to finalize the EDM process for the prototype NGV production. You can see the cooling slot there that's been produced by the EDM process, and the cooling slots in the back of the vane are also produced in a similar manner. These high performance, high integrity turbine components are now cost effectively produced right here by the Hill team at PC1. Over the past 6 months, the Hill team has developed all aspects of the investment casting process for GT50's nickel-based superalloy turbine blades, covering wax pattern production, block and shell creation, casting and inspection. The process now produces consistently high quality gas generator and power turbine blades with one minor defect, a localized failure to fill in the blade's fine trailing edge, resulting from a localized cold shut due to insufficient mold heating caused by a temperature limit in our existing furnace. This remaining minor issue will be resolved over the next few weeks with the arrival of a new, higher temperature mold heating furnace. Once fully filled, the blades will complete inspection, heat treatment, and grinding for use in the prototype engine core. The current blades already meet tight form and profile tolerances, with wax patterns currently being adjusted to compensate for the last of the casting shrinkage, ensuring as cast blades match the design specifications precisely. The gas generator turbine disc has been optimized for strength and life and configured to suit the latest secondary air system. All of the lessons learned with respect to component and assembly balancing have been embedded in the design to ensure that the gas generator can be balanced properly to run smoothly in service. The disc is manufactured from a forged nickel alloy, with the profile being turned from solid and then the precision fir tree route being cut to exacting tolerances using EDM. The EDM processes employed to machine the fir tree is currently being optimized to improve the positional tolerances and eliminate any evidence of a recast layer. Test pieces have been prepared to carry out the metallurgical inspections of the first tree post-machining, and the final optimization of the machining process is underway to robustly hit the exacting tolerances every time we make one. To ensure smooth operation of the GT50 engine, the gas generator and power turbine rotors must be balanced so that their center of mass is within just 1 micron of the rotational axis. This is achieved by machining parts to extremely tight tolerances, individually balancing components, and then balancing the assembled gas generator rotor together. Curvic couplings, which act as axial gears, lock the components together along the rotor shaft and transmit the torque, requiring extremely precise manufacturing and consistent circumferential positioning during assembly. These couplings are repeatedly assembled and disassembled during manufacture to remove high spots on the tooth faces to ensure consistent seating for when the curvics are disassembled during maintenance or overhaul operations. This meticulous engineering is critical for proper engine function during testing. This is one of the first gas generator curvic couplings that fully meets the necessary dimensional and surface tolerances that will allow the rotor to be properly balanced. Once we've completed this curvic coupling, a dummy rotor will be produced in low-cost stainless steel to validate the rotor balancing strategy rapidly and inexpensively. We'll soon have completed the last few nuanced design details on the final parts for the engine core and formally release them for prototype production. The team will then focus on defining the engine test program, the required instrumentation, and designing the test rig to allow the testing to be carried out. As with any complex testing program, the testing follows a building block approach, validating the function and performance of each part or subsystem, and then building complexity gradually, ensuring that any problems discovered can be rapidly traced to cause and resolved with the minimum of complexity. So far, you've seen us develop and test the engine combustion system and control logic. You've seen us test the starter generator and the power management system. You've seen us start the testing on the engine drive, validated and tested with the simplest set of test hardware. This makes stripped down inspections, modifications and iterations as quick and inexpensive as possible. The gas generator test will, however, be quite exciting. Without the power turbine to absorb the energy produced by the gas flow, the engine will expel around 2.5 kilograms per second of high pressure air at about 800 degrees Celsius and close to the speed of sound. As such, a fairly involved test rig and containment structure will be required to safely carry out the testing, initially on the gas generator, but then extending seamlessly to the full engine. The initial functional testing will proceed in stages, validating the various modes of operation, initially starting with cold cranking, then engine ignition, then self-sustaining, and then operating at various fixed speeds across the operating range. The next stage of testing moves on to explore the maximum rates of acceleration and deceleration that the engine can sustain without surge or stall. We'll then carry out temperature surveys to support the lifing calculations of the final production engine, and then we'll repeat all of these tests with the power turbine and drivetrain attached. Our composite rotor blades are crucial to delivering HX50's high performance, benign handling characteristics, and a 20,000-hour blade TBO, along with a class-leading smooth ride. Over the course of the last 6 months, the team have completed the design of our prototype main rotor blades, optimizing the aerodynamic, dynamic, and structural design of the blades, and then delivering a practical blade for volume manufacture. The HX50 main rotor blade uses a conventional compression molding process in closed metal tools with an out-of-autoclave pre-preg carbon and glass fiber material. The blades employ a mixture of biaxial and unidirectional material to tailor the required stiffness and mass properties along the length of the blade, and are constructed with a hollow spar and a foam-filled trailing edge. The manufacturing process has been optimized for higher volume production and is designed to be a one-shot molding rather than a bonded assembly. The thick leading edge erosion shield is manufactured from stainless steel to provide erosion and impact protection to the core composite structural elements. Tracking and balancing the blades is accomplished with trim wedges and span-wise and cord-wise balance weights. HX50's main rotor blades are manufactured in aluminium machined metal tools. All of the tooling has been machined from solid here at PC1 in segments and then assembled into the upper and lower halves and mounted onto a rigid handling frame. The assembled tool halves are then pre-finished, finished and polished on the gantry mill as an assembled unit to ensure a flawless surface finish. This is the very first prototype HX50 main rotor blade tool, and you can tell by the amount of swarf everywhere, it's literally finished machining about an hour ago. The next steps are for the tool to be lifted out of the gantry mill, cleaned, degreased, and then fitted out with its heater elements and insulation. Each tooling half is equipped with 15 electric cartridge heaters under PLC control that use integrated thermocouples to carefully control the temperature profile throughout the cure cycle. This ensures uniform heating for a carefully controlled cure, and tooling insulation helps to reduce the process energy consumption. Given that the required temperature profiles impart differential thermal expansion between the tool and the carbon blade structure, a spring-loaded relief is provided at the root end of the tool to prevent unwanted thermal stress or distortion of either the blade or the tool. This tooling solution is compact, modular and readily scaled up to support the required production volumes for HX50. Over the course of the next 2 weeks, the upper half of the blade tooling will be completed and the first full blade tool assembled so that the first HX50 rotor blades can be produced. The first blades will be used to train the manufacturing team and to optimize the production process to ensure that all of the structural and geometric design features of the blade are correctly formed. Extensive cut-ups of the initial production blades will be carried out and careful inspection and measurements made to validate the production processes. Any manufacturing defects found will be used to calibrate the non-destructive testing procedures that will be used to inspect the production blades once development is complete. When the blade manufacturing process is deemed to be sufficiently controlled and effective, the blade-to-blade variability can be assessed to validate the adequacy of the balancing hardware installed in each blade. The initial blade testing will be carried out on the root end fixture and the various structural sections along the blade to validate the mechanical performance statically, dynamically, and for fatigue and impact. The production of the first state-of-art composite main rotor blade represents yet another major milestone for the company, bringing together years of design and process development to deliver a next-generation helicopter for general aviation at a price that the market can afford. HX50 is unique amongst light helicopters in that it has a retractable wheeled undercarriage as standard to improve cruise performance and aid emergency procedures training and ease ground handling. We've now completed the design of the production intent wheeled undercarriage system and are about to release the first full prototype system for production and testing. The all-new wheeled undercarriage system employs a robust oleo-pneumatic strut designed to limit heavy landing loads to 3G to protect the airframe structure. Actuation is via a dual redundant telescoping electric actuator that eliminates hydraulic leaks, locking mechanisms, hydraulic system components, and significantly simplifies installation and maintenance, as well as deploying the gear in just 6 seconds at any speed up to 120 knots. Each main gear is equipped with floating caliper disc brakes, which are designed to fully arrest the helicopter at maximum gross weight from run-on landings at up to 40 knots. The castering nose wheel is fitted with a selectable caster lock and is self-centering upon liftoff. Sensors are provided for uplock, downlock and weight on wheels, and all undercarriage bay doors are opened and closed directly by the landing gear actuation. Both retractable wheeled undercarriage or fixed skids can be fitted to the common Gen 2 fuselage architecture. The fixed skids are an elastoplastic design that absorb impact energy by plastic deformation rather than oleopneumatic dampers, and therefore result in 33% higher landing loads. The production skids have been modified slightly to ensure that they fit in a conventional shipping container and readily accept over-center wheels for easy ground handling. The skids are an aluminium tube construction with a lightweight aerodynamic fairing and conventional field-replaceable hardened steel wear shoes. Protection against ground resonance is provided by careful dynamic design of the aircraft and through the use of elastomeric dampers in the skid mounting points. While the skids limit flexibility on the ground and reduce the cruise speed and range, they do offer simplicity and a significant 10 kilogram weight saving over the wheeled undercarriage. The wheeled undercarriage is currently going through the production release process, with the skids expected to follow over the next few weeks. Once production is underway, the undercarriage team will develop the test rigs required to carry out the testing and qualification of the landing systems as soon as the conforming prototype units are available. The required test rigs include the undercarriage drop test rig, the wheel and brake test rig, and the actuation deployment test rig. Each undercarriage system will be subjected to static, dynamic, drop and endurance testing as per the certification requirements. Provision in the Gen 2 fuselage and the landing system design are being made for the emergency floats, the HeliMove system and the removable bear paws, and the detailed development of these systems will follow the qualification of the baseline systems. By virtue of its self-contained nature, the first element of the Gen 2 fuselage to be prototyped and tested will be the complete tail rotor assembly, comprising the tail boom, the horizontal stabilizer, the tail rotor assembly and drivetrain, and all mounted electrical and avionic systems. The updated tail boom structure is molded in two halves, creating an efficient torsion and bending section to support the tail's flight loads. The extension of the engine deck from the main fuselage into the tail boom is retained as a feature in order to provide a logical and accessible path for the tail rotor drive assembly and to protect the upper structural surfaces of the tail boom structure from the exhaust heat. The Gen 2 tail assembly includes updated horizontal and vertical tail geometry with the angles and area schedules of the stabilizers optimized for stability and level cabin attitude in high-speed forward flight. The forward element of the anti-collision light and the port and starboard navigation lights are now integrated in the tip of the horizontal stabilizer to make it simpler to demonstrate robust compliance with the view angle requirements to eliminate forward glare resulting from the nose-mounted forward anti-collision beacon. The VHF COM, transponder, GPS, ELT and magnemometer installations have also been developed along with the electrical cable routings and flight control interfaces. The tail boom assembly will be the first element of the Gen 2 fuselage to be manufactured using the new pattern and tooling processes. It will also be the first part of the structure to be CNC kit cut and precision laminated using laser ply placement quality control. Significant material qualification will be carried out at coupon level on the composite components manufactured from this first batch of tail booms to ensure that the manufacturing processes are actually delivering the material properties expected from the material qualification program being carried out at the moment. The tail boom assembly will then be the first element of the structure to undergo full structural rig testing statically, dynamically, and for impact and fatigue at element, subcomponent, and then full assembly level. Once the structure itself is qualified, then the tail boom assembly will be used as a test rig to qualify the performance of the tail rotor and the associated drivetrain. Another area of the airframe program that's finally nearing completion is our crash-worthy crew seat. Extensive practical development has been carried out optimizing its comfort, trim, production approach for cushions, for the composite and metallic structural components to ensure the best possible fit for the widest range of customers. With acceptable comfort, trim and styling and a viable manufacturing approach, we've now been able to finalise the structural design and dynamic characteristics of the seat ahead of final analysis and testing. Using advanced FEA, including a digital crash test dummy, we're currently optimising the seat's laminate, structural components and connections for optimum occupant protection. During this optimization, we've been able to reduce the loads in the occupant's spine, reduce the required seat stroke and eliminate the tendency of the occupant to submarine under the seatbelt due to deflection under dynamic loading conditions. The production intent seat now meets all of the certification requirements and is on budget for cost and weight. And importantly, yes, it is really comfortable. Over the next few weeks, we'll complete the final structural optimization and then the production crew seat can finally be built, tested and qualified. All HX50s are fitted as standard with impact-resistant windshields, as the consequences of a bird incursion at high speed are potentially catastrophic. One of the unique challenges for installing impact-resistant windows in HX50 is that to maintain the clean aerodynamic exterior, it's highly desirable to avoid external mechanical fasteners. Therefore, we not only need to develop the manufacturing processes for polycarbonate window panels themselves, including the relevant tints, UV, IR, anti-glare and hard coatings, but also a bonded joint configuration that was sufficiently robust to cope with the large-scale deformation that occurs during a bird strike. We've been carrying out extensive material testing on various candidate obscuration band materials and structural adhesives to determine the performance limits for the adhesive chemistry. In parallel, we've been carrying out advanced structural simulations of representative bird strike scenarios to optimize the joint configuration around the primary windshield. This work is still ongoing, but the current indications are that we expect to be able to make the purely bonded connection work, making HX50's impact windscreen installation elegant, lightweight and cost-effective. It's not an area of the programme that often gets reported, but HX50's electrical system is now maturing nicely with a significant proportion of the systems now integrated here on the electrical test bench. The high voltage side of the electrical system comprising the starter generator and the power management unit is now operating effectively on the test bench down in the high-speed test lab. Here in the avionics lab, we've been developing the low voltage side of the electrical system, including all of the fine details associated with implementing the electrical system on the aircraft. The wiring loom, the associated connectors, the P-clips, the bulkhead connections, all of the cable management, the cable labeling. All aircraft wire is white, so it's vital that we label each and every wire that goes from component to component. The essential and non-essential buses are being developed. The aircraft battery, the circuit breakers, the relays, the annunciator panel and test circuitry, the start panel, the avionics harnesses, and the integration of the COTS avionics units. This test bench provides functional testing of the low voltage electrical system to iron out all of the system level issues and core functionality. This includes the start panel switchgear, backlighting and wiring harness, the annunciator panel and test circuitry, along with its loom integration, the circuit breaker panel installation and its loom integration, the essential and non-essential bus functions and their loom integration, the full HX50 lighting system. This has already been optically tested for performance and is now being tested as part of the broader electrical system. We've also integrated all of the COTS avionics devices and their relative connections along the avionics loom, along with antennae. Once all of the electrical systems have been integrated and the final wiring runs completed in the airframe, the first prototype harness can be manufactured with the correct cable lengths ready for fitting into prototype number 1. This is the production intent Hill digital cockpit system, now running on target hardware and being connected to all of the peripheral devices. Eric, why don't you give us a quick run through what we've got developed here?
Absolutely, let's go for it. Let's start right in the top here of the screen. We have very clear, bold airspeed indicator with both a needle and the digital printout. Right in the center, we have the attitude indicator with a big artificial horizon filling the whole screen, very clear pitch ladder, roll indicator, side slip indicator. At the bottom, the horizontal situation indicator with the compass, as well as traffic scope that shows any traffic threats that you can change the scale of. You also have a wind bug on the compass that shows your wind direction and speed. Off to the left, we have our barometric altimeter. Now this is a little bit different because we are, instead of having your more traditional altimeter with multiple hands showing your thousands, etc., we have a single hand and then a digital printout in the center. As the needle swings around, the labels will dynamically update so that you have always the whatever scale that you're at showing whenever the needle is pointed at that position. So right now we see 1000 here, but as this moves, if it does a couple laps around, you'd see 2000, 3000, etc.
Yeah, so the whole clock face represents 1,000 feet,
Yes.
and you're just sweeping through the next 1,000 feet as you climb or descend.
That's
so
right.
it's really clear to see where you are, and it's really easy to read.
So as opposed to having to interpret various hands like a clock, you have a single needle you need to pay attention to.
Fantastic. And for customers that are opting for the radar altimeter, where will that information be displayed?
So the radar altimeter will be printed as just a digital printout underneath
Yeah,
the main gauge there.
great. I love it.
Off to the left, we have the vertical speed indicator. So this is again a dial and then the digital printout in the center. And this will change colors based off of your flight state. So if you're really low airspeed and descending quickly, then it will warn you for, in various other stages if you're climbing too quickly. Down to the bottom here, we have our autopilot mode selector buttons, so we can change different modes of the autopilot with those. Moving down to the radio bar, we have our transponder settings here, your squawk code, ident button, and then two large comm boxes, COM1, COM2. Both of those have your active and standby frequencies. Now I can slide over or drag over any of these boxes, and I can change, in this case, the volume setting for my comm radio, for my COM1, or I can tap into it and it will open a comm edit mode. Again, it shows a smaller volume slider here on the left. I've got my active and standby with a swap button, and then I've got lists. So this is currently showing my nearest, but I can change this to be favorites or recents, that sort of thing. So I can select one of these, it puts it into standby, swap it in there, and then click that to enter.
And then from a flight planning and preparation point of view, the favorites list is synced with the Hill app.
That's right.
So that you can prepare your frequencies at home while you're doing your flight planning, and they'll automatically sync with the system so that they're waiting for you for your flight. No more scribbling on the backs of pieces of paper.
Absolutely.
Very good.
So moving up here to the engine and the tacho side of things, we have our large first limit power indicator. This shows your percentage of your power available. So 100% being max continuous power, and then the moment you go above 100%, you're into a time limited range. And so when you go above 100%, it will show you that you are, if I just exercise this a little bit here, I'll move it above 100%. You can see it turns amber, and I see this sort of progress bar, this circular progress bar that's disappearing, showing my time remaining. If I increase the power a little bit more, it goes a different color. This is the 30-second range.
Okay, so you're always aware of how much time you've got to be within the aircraft's duty cycle and POH limitations, and that happens dynamically whenever you do it.
That's right.
Great.
And then you have fuel on the bottom here of this gauge, so just shows you your percentage of fuel. And this, as we've shown before in previous version, you can toggle this between different units, whether you want it as a volume or a mass or percentage. You can just tap to change those units, or just configure it in the settings on the IPI.
And then at the top of the bar, we also get our range and our endurance calculated dynamically.
That's
using
right.
your current ground speed and your current fuel consumption, so that you always know what your fuel remaining amounts to in terms of operational flight parameters.
Yeah, it just extrapolates based off of your current setting, how much further you can go.
Great.
With that. And then the tacho off to the right here. So this is a combined engine and rotor tacho. So you have two 2 needles, and then the rotor speed RPM percentage is displayed in the center as a digital printout, and then the engine RPM is displayed over here. Now if I wiggle these with my controller here, I can show you the rotor speed is the one that's on the inside, the bigger needle, and if that goes out of range, then it turns colors. So if that's under, then it goes red, or above, it
So
goes red.
this is currently configured so that a high rotor speed will drive the needle high, and a low rotor speed will drive the needle low.
That's right.
Okay.
And similarly with the engine speed, which is the smaller needle kind of behind the rotor needle, is shown there.
And the whole gauge is set up just to focus on the range of RPMs that are most likely to be encountered during flight. So it's just the useful range with a bit of margin either side.
That's right.
Great. It's looking great.
So up to the top right-hand side, the top right-hand corner, we have our enunciation and warning area. So just at more of a high level, anything on the top left-hand side, we have a space in the corner here for notifications and widgets. One of these widgets is stopwatch, for example, so I can set that going and I can minimize it or maximize it again. We also have things coming in for accepting flight plans that have been pushed over from the EFB app. Other notifications would be shown there. On the upper right-hand corner, anything shown in this corner aside from this, just the trip information stuff on the very top, anything that shows up there in the upper right-hand corner is going to be a very important message, warning and enunciation, something's gone wrong. So if I just enable some of these so you can see, this is an engine fire. So you have your primary sort of resolution or box to advise you on what you should do to react to whatever the state, whatever has gone wrong.
So this is the guidance straight out of the pilot
guidance.
operating handbook that's paraphrased so that you can just do it immediately. You don't have to look or remember anything, just do what it says on the screen.
That's right. And then if there are any fault states, whether it's an amber or a red warning, those will all show here. So if I just enable a bunch of them here, you can see multiple. And so you have a space for about 7 of them there, and it will always show your highest criticality enunciations as priority. And then it will summarize whatever is the recommended reaction to that, the recommended guidance from the POH as to what your reaction to that would be a pilot, whether it's landing immediately or landing as soon as practical, etc.
Yeah, and these are in addition to the simple hardware for the enunciation panel.
That's right.
So you've still got your wire and a bulb, things that are really fault tolerant.
That's right.
On top of that, these are just to make the workload of the pilot lower, to make it simpler to do the right thing.
That's absolutely right. And if you don't like this sort of message there, you can always get rid of it. But you can't remove these flags, basically those enunciations as you can't remove these enunciator lights when they're enabled.
Yeah, and then the traffic display that we've got in here, that's ADS-B traffic, isn't it?
That's right. Yeah, so you have your scale, which you can drag to adjust the scale, whatever. This is my current position in this demo is at Heathrow, so we see a bunch of airliners coming in a row here into landing. But it obviously show different iconography for different types of aircraft, whether it's a helicopter or if it's a large plane, a smaller plane, there's different icons we're using to help provide that extra information so that you know what sort of traffic is around you.
Fantastic. It looks great. Should we go and have a look at it in the lab and look at some of the hardware?
Sounds like a plan.
Let's go.
Here we are in the avionics lab. We've got all of these systems laid out on the bench for integration and testing. We have the cockpit display system here broken out into its individual components. Of course, your screens that you interact with as a user. Behind the scenes, we have different processors boards that we're actively developing and integrating. Starting with the primary display processor. This is the main component of the system that brings in data from all the peripheral systems, concentrates that data, and then sends it over to the secondary display processor, which renders that into the UI which you see on the display. Now, the primary display processor is also actively checking the output of the secondary display processor to make sure that it is correct. Now, if it detects any sort of error, whether it's just completely crashed and it's not even showing anything in the first place, or if there's information that is misleading, then it will step in and display the reversionary UI, which I showed you in the helicopter. Now, it's not just checking a simple sort of am I alive sort of situation. It's actually checking pixel by pixel the video output and checking to make sure that what is displayed on the display that the user, that the pilot sees, is accurate. And then if there's an error, then it can intercept that and put up the reversionary UI. This is all connected to, of course, the various peripherals on the aircraft, whether it's intercom, radio, transponder, ADAHRS, GPS, all these different systems. So the primary display processor is the primary interface with all of that. So these boards will all be packaged up into a single integrated display unit. You'll have your display and your primary and secondary processors on a motherboard mounted behind that. And there'll be 2 of those per aircraft, one for the right hand, one for the left hand, which offers a little bit of redundancy there. All right, so let me show you some of the systems that we have on the bench here. I'll show you demo some of their functions. Starting with the annunciator panel, this is the one that's above the primary flight display, just a very simple redundant system connected to the sensors for various annunciations, fault states. So I'm going to turn on one of these, and we should see it light up on the panel there. As you can see, we have battery temperature, so indicative of battery temperature outside of limits. So that's all hooked up here on the bench. We have our ADAHRS. So this is piping in your attitude, air data, your compass, all of that sort of thing into the DigiCockpit. So if I move this, you should see the pitch and roll changing there. So that's all interfaced and it's all connected. We have our intercom that connects the headsets as we have mounted here. We have comm radio. We just have one currently mounted, but there will be 2, and then the transponder. And then moving back to the GPS. And then as we go even further back, of course, we don't have the full length of however long the tail section would be, but we have the magnetometer here for the magnetic compass. That's actually going to be a bit further back to be away from magnetic disturbances. Here we have a technical mock-up of our cyclic grip. This is right at your fingertips, easy control actions that manipulate the core functions of the DigiCockpit. So just describing the functions here, we have on the left-hand side with your thumb, you have an autopilot mode selector switch. So if you press up on this, it will advance higher into the modes. So if you press once, it will turn on your stability mode, your attitude hold mode. You press again, then it'll activate your altitude mode. And then if you pull down, if you hold it down, it will turn off all modes. And if you just tap it once, it'll just notch down to the next lowest mode. Right in the center, it's not really shown very well on this mock-up, but it'll be a very big button for your push-to-talk button for the radio. And then above that, you'll have a list button that will open up the list function, the comm edit function on the PFD, or a swap button. So if you want to swap your your standby frequency into active, you press the swap button. On the right-hand side, we have the landing light switch. So in the sort of the normal centered position is off, and then if you push it up, that's on, and then all the way down is a special strobe mode where the landing lights blink for helping with deterring birds, that sort of thing. And then on the front of the grip, which isn't on this one, but I have it on here, is the trigger. So the trigger is your force trim release for the autopilot. And so you'll have this on both the cyclic and the collective grips, will be the force trim release. When you press, it will detach, the autopilot actuators will detach, and you'll be able to move it without any of the control forces fighting against you. And then you can release it to set the new datum, or you can move it while keeping the control forces and just tap it to set a new datum.
What started as an idea and became a dream for many is now hardware, and piece by piece, that hardware is being proven. HX50 and GT50 are being forged into reality by the sustained and determined efforts of our incredible team, powered by the support and belief of our wonderful community. Thanks for your time, thanks for your support. It's now time for some questions.
Wow, welcome everybody. It's amazing to have so many people joining from all over the world as usual. Well over 1,000 people currently watching as Jason gives another incredible update. Jason, this was an exceptional one, very technical, longer than usual because there's so many things going on, and it really got me jazzed up. It got me excited about getting my helicopter and getting it to fly it for the first time. It's so neat to see what's been going on, in behind the scenes for these months now. Just so many different components and moving parts that are happening. And I want to actually thank you for taking the incredible amount of time that it takes to give us these updates. I know how busy you are and how much effort you have to put into making these updates. And so I want to thank you for that. And I just want to welcome everybody being here. Again, we have the agenda for today is an AMA. So Ask Me Anything session. You guys have the chat right there that you can ask any questions that you want to directly to Jason. And so you're welcome to do that right now. Start posting those questions in there, and Jason's going to be able to answer those over the next hour. So we're going to have 1 hour, and we're going to close the session off of questions that Jason's going to be able to answer for us. And so we're going to dive right into those right now, and then looking forward to going on to all the different things that Jason's going to update us on. So Ruben, why don't you go ahead with the first question?
All right, here we go, Jace. If you're ready, first one comes from James Page, and he wants you to describe how you're going to access the pre-flight for the engine rotor head.
Yeah, so what you don't see on the helicopters that are behind me at the moment is the split lines in the cowl panel. So those there's a split line that runs essentially in line with the main rotor shaft and opens those cowls. So the engine cowl slides backwards, and then the main rotor pylon cowls will open up, and then you can get at all the flight control actuators. You can see up and get at all the pitch links, the pitch horns, the strap packs, lag dampers, everything. So once you climb up and open those cowls out, it's easy to see everything. And then on the top of the donut, as we call it, there's some access panels up there as well, mainly for maintenance, but you would be able to use those for inspection if you wanted to.
Very nice. Next question is coming from Drew, and it's a question that's been asked in the past, but it'd be good to go over it again. He says, will there be a camera integration system, like a GoPro style, that you're going to have different cameras in different parts of the aircraft, inside, outside, etc., and then an easy way to be able to get that video footage, put it together in a simple way, to be able to share it or to be able to go through and analyze it?
The answer to that is a partial yes. So we've obviously got the cameras that come standard with the aircraft as part of DigiCockpit and the overall surveillance of the aircraft and its well-being. They're fully integrated with the app, fully integrated with the DigiCockpit. We're also very aware that camera technology, communication and social media technology moves far faster than aircraft development. And so what we've elected to do is make sure that there's plenty of locations around the cockpit and around the DigiCockpit where you can affix localized mounts to put GoPros or other devices that you might want to. And there's lots of USB-C ports around the latest version of the cockpit interior as well. So we've provided lots of locations where you can affix GoPro style cameras, lots of places where you can power those via USB. But at the moment there isn't any plan to pipe that directly into the DigiCockpit, because really what we need to do with that is keep it super simple and super high integrity. The aircraft is an aircraft. But we want it to be able to be used as flexibly as possible. So we'll make it easy for you to mount things to it that you're likely to want to. But we have to have a cut-off point somewhere with what's part of a flight system and what's part of your fun systems.
All right, and Drew has another question, and this one is regarding the flight simulator. So what are your plans on packaging a flight simulator, and any level of hardware would be planning to integrate with that? So I'm thinking here it'd be more of a hill simulator. What are your plans for that?
So we don't have any plans personally to build a mechanical simulator ourselves. There are lots of great companies out there. We've got lots of customers that are involved with great companies out there that have expressed interest to do that kind of work. So we will provide licenses for people to use our hardware, use our interfaces, use our DigiCockpit to make us higher fidelity training aid or toy version, or a gaming simulator as they possibly can. So things like the cockpit, things like the stick heads will make that sort of hardware or representations of it available to people, but it's not something we'll do in-house. We are very, very keen on the use of flight simulators as part of the training syllabus. There's lots of things that you can do with modern flight simulation that you really wouldn't want to do in a real helicopter, and those are areas that we're keen to grow into. But at the moment, as you can imagine, we're really focused on getting the engine running, getting the first aircraft into the air, and then getting through the approvals processes and scaling up to manufacture. So some of these things that are interesting, they are important, will follow some way down the line. In terms of the overall simulation landscape, there's one piece of the puzzle missing from having a fully calibrated math model for the flight dynamics of HX50, and that will drop out of the flight testing over the coming months. And then essentially we've got a math model that can be fed into the X-Plane and the Microsoft Flight Simulator, the versions for the gaming platforms as well.
Okay. Graham's got a question, and it involves what you're talking about with the gear case. So just what you mentioned in the update, that the gear case and the gears need to be able to withstand 500 shaft horsepower, which is what's going to be coming through them. And it says, made me wonder how much power do you actually rate them for? So is there an industry standard and an engineering equation that you follow? So i.e., are they rated to, let's say, 600 shaft horsepower, but they only need to be handling 500. So that's basically the question.
So our gearboxes are designed notionally for a 20,000. Our gears are designed for a 20,000 hour life, and so are the bearings. And so they're designed to handle 500 horsepower for 20,000 hours, and then we downrate that to the 5,000 hour that we make available to the customers in the first instance. And then as we develop more and more experience on the bench, as we have a look at what the gears look like and we can inspect them when they come back after their first service life, we can look at whether it's worth looking at extending the lives of those components, or given the low cost of manufacturing these to us, whether we just play it safe and keep that margin to have the highest possible the lowest possible failure probability that you could ever have across the large fleet that we'll end up with. So the gears are fundamentally sized for a fatigue life, for doing a duty for a particular number of hours. If you looked at what load they could actually carry for shorter periods of time, it would be enormous. So they've got a very, very high static capability compared to the fatigue life that they're rated on. So the gears are flat rated at 500 horsepower, but they're flat rated to do that for many more hours than you'll ever need.
Very good.
Before the next question, actually, Jason, I have another follow-up one regarding this, because we have repeat questions about this subject of the lifespan of the parts. How are you going to be able to have such a long life for the engine and the rest of the machine? So can you elaborate on that? So people probably don't have this good visibility that you just described, that there's a big margin of safety of actually what you're testing and where you're actually putting out as the life span of that part. How do you manage that? Because there's a big margin of safety, correct?
Yeah. So the way this works is the aircraft has a duty. It has a set of flight cases, a set of loads that it's expected to do, and we can create a duty cycle that represents how this helicopter is going to be used. Now, to do that, we take a very, very conservative view on the punishment that these machines are going to get in service, and that forms the basis for our start point for how we life these components. And then for every established area of the aircraft, so if you take gears, for example, there are AGMA standards and lots of internationally recognized ways of assessing the performance and life of gears and then calculating their duty and how they'll perform in service. We then design the gears to using those relationships, those accepted practices. We do lots of finite element analysis on them, and then ultimately you build them and you test them on the bench. And the life that we will be allowed to put forward to the customers is the life that we will have demonstrated using the worst case cycle on the test bench. So the way it works is we design what we think the duty is going to be and what we think the loads are going to be using our best judgment, and we clear the gearbox for a number of flight hours, and then we go off and fly all of the maneuvers and use those measured loads to then create the sort of TBO lives that the components will see in practice. And those methods, those approaches are very typical of all of the mechanical components. And it's very similar with the structure and with the rotor blades. So if we take the structure first, if you look at the airframe structure, you have to consider the landing loads, the flight loads, the ground handling loads, all sorts of different ways that the structure can be loaded. We calculate what they are. We calculate what we consider to be the worst case duty, how many times those loads are going to be applied in service. And then we calculate the life that we expect the structure to have. And generally with these things, with the exception of the very big loads that happen relatively infrequently, you're usually trying to design these things to be non-damaging. So for components that are made out of steel, for example, they have an endurance limit. So this is a level below which cyclic loads don't do any damage to it. And so for the individual passage of gear teeth on each other, the stresses that you get at the root and the contact stresses, those are designed to be non-damaging because they happen so often that if they were damaging, the gears would fail really quickly. And so we try and do that as much as possible. But where it's not possible, we calculate the amount of damage each one of these load applications does, and then from that we get an estimated life. And then we go and fly the demonstrated aircraft, measure the loads, and then verify that load, that life on the bench by subjecting each and every one of these critical components to the number of cycles plus a healthy margin that we think these things, that we're trying to clear these things to withstand. So that's the general approach to the fatigue side of it for the mechanical and the structural components. It gets a little bit more involved with the rotor blades because, of course, the rotor blades are very much dominated by the flight mechanics and the structural dynamics, how these things move and bend and react to the complex environment that they live in. So we can predict those loads using comprehensive aeromechanical models, and then that allows us so that we can essentially simulate the interaction between the aerodynamics, the flight dynamics of how the aircraft flies, and then the resulting loads and vibrations that we get through the rotor and into the aircraft. We use that plus some safety factors to calculate the initial strength and design of the aircraft. We clear the prototype aircraft for flight based on using those loads and testing those on the ground. And then one of the first things we do when we go flying is go and measure what all of those loads are for each of the maneuvers, each of the CG positions that the aircraft's going to be cleared to do. And then those measured loads are the ones that we use to do the life extension testing on the bench. So that's the structures, the rotor blades, and then for the engine, it's basically the same process again. We test, but the thing you have to understand about our engine versus the most popular light engine is the early engines that you find in some of the older 5-seat helicopters were a much lower level of technology than what we've got in GT50. So the thing that really hurts small gas turbine engines is twofold. It's the huge temperature gradients that they see when you turn the engine on and heat it up to its operating temperature. It's the huge differential thermal expansions and loads they see from the areas where we're pumping cold air to keep them cool to the areas that are subject to the burning gases and are much hotter. And the stresses as those components pull against each other are very high. That's one of the contributing factors to why you've got a start-stop cycle limit on your gas turbine engine. And the other factor is the cycles of the N1 and the N2 rotors spinning up and down. Now, in the early technology engines, the turbine discs, for example, were cast as one piece. They were solid blisks, and that means that at the core of the disc, you're pumping cold air to keep it cool, and then in the blades, you're having all the hot combustion products rush past them, and you're forcing them to be hot. And those differential stresses, coupled with the variations in centrifugal loads, give it a really, really hard life. Later generations of discs introduced slotted discs and drilled into discs, into blade spaces to try and reduce those effects. And the next generation of blades, which is where we are, have got fir tree roots and different material selections for the blades and for the discs, so that we can really decouple the thermal field and the stress field between the blade and the root, and use more appropriate materials in both areas. So that's just one example of the things that we do in the engine. There are many, but this engine is just a more modern engine than the most prevalent engine that's in this space, and so it can do more because it's just a better design. It's a more modern approach. And the other thing I would say is that 5,000 hours isn't a lot of hours for a gas turbine engine. Okay, it's the cycles that are difficult. It's not the hours. And if you look at our engine at sea level at 400 horsepower, which is its cruise setting, most of the hot bits have got an infinite creep life. At that place, to all intents and purposes. It's very low temperatures in the engine, and at those points the engines are not working very hard. So again, it's just a case of understanding where these limits are, setting the engine up properly for long life and capability, and then just diligently working through the testing and proving off each of these points. So it is by no means a stretch. And I think with the latest version of one of the Safran engines that's just been put in a new helicopter has got a 5,000 hour life and 10 to 20,000 cycles. So it's something that's always been possible.
Very good. What a masterclass of the lifespan of great. Thank you for that. Next one is from Christopher.
I'm exhausted after that.
I can see that every single detail. It has an explanation, and you actually did explain this to me personally, and I wanted to have this available for the audience because I think it's a very common question people ask. They don't understand initially, and you give a very complete answer. Thank you for that. So next one is from Christopher. Will the HeliMove have a power port to charge the battery? Where will that be located, and what type of device will be needed to charge it?
So you asked me this question last time, and I promised that I would go and look it up, and I haven't. The power port is just by the pilot's door, in a similar position to what it is on the 66. So there's a power port there that takes a low voltage 28 volts source, and also a domestic socket source as well. So we've got two ways of charging the HeliMove and the onboard electrical systems through the pilot door.
Okay. And Tokyo Blue is asking, are there any hopes of partnering with pilot schools for training in any capacity?
Absolutely. We've consistently said that in terms of our company growing, we need great people everywhere. We never intend to be a training school. We'll offer factory courses in the early days, and we'll always do a factory safety course. But in terms of ab initio and continued pilot training around the world, that needs to be done by the experts in each local area. So we will help by producing centrally sourced training materials, all the rich media stuff, all the simulation training aids, and anything that we can to help standardize training standards around the world. But we're more than happy to work with suitably qualified training schools around the world to support the product in any way they can.
All right, next one from Leo is, one of the most important aspects of GA is fun, engaging adventures. Considering the huge significance of aerodynamics in the design of the HIL HS50, will there be options for carrying external loads such as mountain bikes, snowboards, and even dirt bikes, taking into account total takeoff weight and reduced range?
Absolutely. So bear in mind HX50 and HC50 are essentially the same helicopter, and HC will be doing lots of interesting jobs in its commercial roles. So underneath the belly of the aircraft, beneath the A pillar, the B pillar, and then the rear bulkhead, you've got a large cargo hook attachment, and then on each of the beams under the belly there are 3 multi-point utility fastening points. So these are locations where we've got connectors, so external frames, external roll equipment can be attached to the floor, and each of those adaptation points just come with a load capability and an interface standard, so that you can essentially bolt anything you want there within a certain volume and within a certain characteristic. So we should be able to do things like ski boxes, mountain bike attachments, external cargo, that sort of thing. So it all needs to be subjected to normal approval process and STC and what have you. But yes, the provision has been made in the structure for those things to happen.
Beautiful. Can't wait for that. Steve is asking, given the recent issues that others have had, have you taken any steps to mitigate the delamination issues with the rotor blades?
The rotor blade recipe that we're using is a well-proven and well-understood recipe. And so we expect our rotor blades to be extremely robust in terms of delamination. And I think the characteristics of properly executed composite, we don't have to do cores. Because I don't want to invest in that stuff until we're almost ready for production. But the problem with metal 3D printing, well, I will start with the upside. The upside, you can make anything and you can make it relatively quickly. The other upside is the mechanical properties are generally better than what you'd get from castings. The downside is metal 3D printed is quite limited in size and the machines are very slow. So as a production process, it's just too slow for the expensive laser printing machines to ever amortize their capital cost. So it's great for extremely high value components. It's great for rapid prototyping. It's really not there for production at our kind of volumes yet. And that's in any of the materials, whether you're talking lightweight alloys, or even the super alloy stuff. It's really interesting, it's really capable. We would love it to work because it'd be much nicer filling the factory with a bunch of things that look like washing machines rather than a pattern shop and a wax shop and a shell shop, and all that stuff's big and industrial and messy, but you really can't beat it for these kinds of components. So we're watching it very carefully. We are using it. We 3D print waxes, we 3D print in plastics, we 3D print in metals, but they're not production processes.
Okay, very good. Tholdor is asking, when we purchase a Hill HX or HC50 here in the US, how does somebody ship the helicopter to the US?
Yeah, we will make that process incredibly seamless for you. So essentially, after the flight test, the aircraft can be either flown away from the factory or it can be made available for collection from the factory, pre-crated and ready to be picked up by a shipping and handling unit. We're working with numerous providers that will provide those services in a sort of white glove fashion to customers wherever they go. So the machine will be in a standard shipping container, all crated and protected properly, and then it's over to the shipping handling companies.
What kind of things need to come apart on the aircraft for it to get created into a container?
We're still playing with that. We're still playing with that at the moment, but it's likely to be main rotor off, blades off, gearbox off, and tail boom and tail feathers off. And main fuselage goes in on its undercarriage then. So the tweak that we've made to the skids is so that we can leave it on its skids, so it can just go in on its ground handling wheels, be strapped down, and it's one less thing to worry about. And then the reattachment of the top is relatively simple, and we're just looking at whether we can position the aircraft in a shipping container to leave the gearbox and the rotor head on as well. We think we can, but we haven't done it yet.
Okay. Right, great. And we are reaching halfway of the Q&A time. So if you have questions, you put it on the chat. We're going to be asking those to Jason. So it's very easy. Just have to fill in that question on the chat. So next one is from Christopher. and he has one that is interesting. And let's see, let's go with it. Any thoughts on reverting to an external engine manufacturer to get these up in the air earlier? Everybody wants it earlier. Then phasing you to your own engine, even if cost is even higher to start with.
No, there's no interest in that. It doesn't work for us now. I can't imagine very many of my customers would want me to double the price of the helicopter. The engine.
That's what we're talking about, right? Actually, that's an important part because we're talking about the engine having an impact pretty much of almost the helicopter cost.
Yeah,
The price.
but people need to understand that what we've built here is a manufacturing platform. The engine isn't just for HX50, it's for the other helicopters, it's for the fixed-wing aircraft. There's a much bigger strategy behind all of that, and that's not a discussion for now, but the engine is the crown jewel of the company. So this development process is going to be hard. There are going to be bumps along the way, but we are going to see it through because it changes everything for the whole industry. So no, I have never ever, not even once, thought about abandoning GT50 and going back to one of the other guys. And I know what we've got in the test bench over there. I know what's coming next. And I don't have any fears about this engine at all. You know, I can't tell you that it's going to be tomorrow, but I've got no fears that we'll do it.
Very good. GS is asking a simple one. Why would I opt for a radar altimeter? Maybe just not understanding what a radar altimeter does.
Yeah, so for clarity, a radar altimeter just tells you your height above the ground directly below you. And some helicopter pilots find that useful information because helicopters tend to fly relatively close to the ground. And so having that direct measurement can be quite useful for you. That's the main reason. They're generally an instrument flight rules tool, but a lot of VFR helicopters do pick them up. I don't know if you want to add anything to that, Misha.
No, I think that's fine. Yep, it's certain operations are useful for it if you're doing LiDAR work and things like that. Sometimes it's useful to have a radar altimeter, but yeah. Good.
Will the landing gear model have an option to remain extended and have skids attached for snow operations?
Not skids, but bare paws. So there's a bare paw kit that when you fit, the gear has to stay down, so it inhibits the retraction functionality of it. So it's pilot fittable, and it gives you a nice big footprint area so that you can land comfortably in softer ground, and that does force the gear to be down.
Okay. Steve is asking, US implemented an ADS-B with ground-based broadcast requiring an underside ADS-B antenna. Canada chose to implement the satellite-based ADS-B requiring a top deck mounted antenna. How do you handle this?
That's really a question for Eric. We have got a number of antennas sprouting all over the aircraft at the moment. So there are a bunch of antennas on the belly now, and there is a provision for a further antenna just in the front of the beak on the cowling on the front of the rotor. So I suspect we've got the antenna for that in place, but I'm genuinely not an avionics guy, so I'll talk to Eric about that and come back to you.
Okay.
By the way, what a fantastic update on the avionics. That was amazing. With that demonstration, it was mind-blowing to see.
I'm going to say we put this video together under extreme duress very quickly, and we've missed a bit of the update on that. And one of the things that we didn't show you was the reversionary interface. So we've now got a reversionary interface that runs on the really high fidelity hardware. So if the monitoring system detects any misleading information, or it's not happy with the functionality of the secondary display processor, then it will immediately switch to this simplified display. But it in its own right looks great. Everything's still in the same place. It's just a stripped back graphical presentation. So I'll do a mini update on the app on that over the next few days and show you that, because that's really good too. And
Great that you mentioned the app.
It's little things like the volume slider, and I don't think we demonstrated there's a brightness slider down the side as well. So if you run your finger up and down the displays, it'll change the brightness of the display. So when you're flying at night and you want to tone everything down, that's pilot selectable. You've got the light sensor built into the unit, so it'll go to its automatic settings, but you can also tune that, and those things are immediately there all the time, so you haven't got to go through 10 menu layers, it's just there. So yeah, all of these things are distilling very nicely now down into the essence of what you want it to be.
Great that you mentioned the app, because actually that's something we always say, Misha and I, in the presentation, that it's unique about the HILT program. Because once you become a client, you are going to be like inside the development team, seeing all the details and the fine tuning of things. And actually I remember, Jason, from the beginning of the program, that some of the features of the aircraft, they actually came from suggestions from the clients. And this interaction at the development stage, an aviation company that has the clients participating and having that knowledge and experience has never been done before. So it's really something I want to emphasize again, unique about the HILT program. Some people ask, how can I get on the app? Well, become a client, it's also going to have the experience of this process.
I'll give you another quick example of that, because it's something that I'm about to do. So we had the actual CAA test pilot visit us that's going to do the approvals flying for us about a week ago. We're very engaged with the CAA at the moment. They're really ramping up the involvement in all areas of the approvals. And he came from a human factors point of view to start with, to review the digital cockpit, because that's potentially one of the more contentious areas. And it's really interesting, because it's sometimes when somebody comes to you with a completely different perception to your own of how things should be. And in the entire DigiCockpit, the only thing that he picked up on that he wasn't sure about was the direction of the needle in the RPM gauge. Okay, so most of my flying experience is on Robinson helicopters, my personal flying experience, where their RPM gauge goes up when the RPM is high and down when the RPM is down. And out of bias, because that's what I've always known and I feel comfortable with, that's what we've done on ours. But the guy from the CIA has got a lot of experience across a much wider range of helicopters, particularly bigger stuff and military stuff, where they tend to have full ring, full gauge RPM gauges that go all the way around. So one of the things that we explained this to him, and we thought the perception of where many of our pilots would be coming from, that would be what they were expecting to see. So I'm going to put that to the customer base on the app, and we'll do a little poll, and the direction of that needle is going to be set by what the customers say and what the general market consensus is. So that's the power of interactivity that we've got with the customer base, and the control they all have over their own destiny.
And it has meaning, because it's not a couple of clients. We're talking about more than 1,000 clients. So it is representative actually of what the market actually wants.
Yeah.
We have the best poll ever of interest, which is 54% of the new helicopter orders placed were HIL last year. So that is an incredible representation that we have on that app, and they can give us incredible feedback as well. Thank you for that, Jason. So the next one is from Harry, and is, as a single pilot operation, if crew is incapacitated, is there any single button to push by a passenger in case of an emergency and the helicopter can land by itself?
So if you choose the 4-axis autopilot, there will be, but not immediately. So we've said from the get-go, the 4-axis autopilot is there to allow us to grow into greater levels of autonomy in the future. All the sensors, all the actuators, all the physical things you need to control the helicopter are built in. And then as we continue the development of the aircraft, we have the opportunity to develop a sort of pseudo co-pilot or a safety pilot function that will get you on the ground or bring you back to a safe location in the event that the pilot's incapacitated. So not from day one, but it will come.
Okay. Next question is coming from Leo, and I think he's hoping that you've had some good conversations with Elon Musk recently. He says, will there be a Starlink native integration?
We're looking at it.
Okay.
coming. It's coming. It's great.
The data,
Okay.
if you think of the DigiCockpit, the video, the streaming of data back to the cloud to allow us to manage the aircraft, the pilot, all the active safety management stuff that we want to do, you need a great data connection. And so we're looking at that at the moment.
Clint has a question from a perspective of 44 owner and pilot. In my 44, in full power, a full throttle, a caution light that illuminates. In my 44, there is a full throttle caution light. It illuminates when you're maxed out the power. And if you pull more collective at that point, you start to get the low rotor. So will Hill have something similar?
We've gone further than that, Clint. So first of all, we've got what we call active power management. So on the Collective, the autopilot actuator provides haptic feedback, so force feedback. So when you pull the Collective up, when you approach maximum continuous, and maximum continuous is calculated from all of the characteristics that affect it. So your N1 speed, your measured gas temperature, your torque limitations. As you pull the lever up, when you approach your maximum continuous power, you'll feel a change in stiffness. To pull the lever up, it'll pass through a notch. And then when you pull it up into your 5-minute or your 30-second ranges, you'll feel different force gradients, and then you'll get an increased tendency for it to pull your hand down as that timer runs down towards 0. So the Collective will talk to you. So even if your eyes are outside as they should be, if you're trying to land in a confined area, you'll be able to feel what your power is, and you'll get physical cues from the Collective when you're running out of time to hold that power level. So we communicate with you directly as you touch and feel the aircraft while you're flying, and that extends across both the cyclic and the Collective. So in terms of things like vortex ring and limit and sort of envelope protection features, all of those are there within the autopilot feature, but fundamentally the haptic power management has always been there since day one. So from that side of things, the envelope is protected. But the other thing you've got to bear in mind, and I should qualify this by saying, if you put enough weight in anything, you'll run out of power. It doesn't matter whether it's the MIL 26 or a 22. You know, everything has limits when you load it enough. The way we tried to pitch HX50 is 5 95 kilo passengers, 3.5 hours of fuel, and you can still blast off vertically. Anywhere up to 10,000 feet on an ISA plus 15 day. So if you've got clean blades and a healthy helicopter, you should never run out of power, as long as you're operating within the pilot operating handbook. It's not like a naturally aspirated piston engine with modest levels of derating. This is a helicopter that's been designed to perform as it needs to for its intended target audience.
Okay, very nice. Jonathan's asking a question, how is the black box being integrated into the system?
So essentially, the data acquisition from the DigiCockpit is streamed out via the app and up to the cloud. So it's essentially like that. So the DigiCockpit itself, the primary display processor, correlates all that data, and then we've got some onboard storage to hold a finite amount of that data, and then that data is passed and sent over through the app up to the cloud and back to us and to the users.
All right. Based on where you are in the roadmap, with the recent and likely ongoing global geopolitical challenges, do you remain confident with the launch date and plan you share?
Yeah, the plan that we've shared at the moment is our best estimate based on the information we have at hand today about when we can deliver each of the next milestones. And we'll continue to update the customer base every time anything changes that. But at the moment, we've got 50% of the engine on the bench. The updated Gen 2 airframes coming together really nicely. We'll have the first rotor blades within the next 3 to 4 weeks, I think, assuming we don't break anything in terms of machinery. The DigiCockpit's in a great position. We're steaming through what was at the outset a near impossible task at an incredible rate. So yeah, I'm confident with where we are. And in terms of the geopolitical factors, they're really not having a great impact on us at the moment. So we're just going to keep our heads down and keep working.
Okay. Next one is, have you been able to find and secure an insurance company specifically for Hill helicopters? If so, can you share expected costs per month or year? Also, will there be any financing options directly from Hill?
So in terms of the insurance question, we will be insuring the hulls directly. We may choose to seek external underwriting for the fleet, but the Hill insurance will be available to everybody everywhere. So that's a piece of work that we've been working on now for the last 2 to 3 years. We're dealing with a number of major insurance companies behind the scenes to look at different ways that we can deliver it. But that will be available before the first aircraft rolls off the production line. So we will ensure that Hill insurance is available. In terms of financing solutions, again, we've talked with many of the usual providers for aircraft finance, and as soon as the aircraft is approved and ready for service, you can expect those normal providers to be forthcoming in terms of offering Hill finance. Yes, absolutely, we will seek to do that internally, but we need to build up the cash reserves first. So that's something that we'll offer later once we've had a few years of production behind us. But in terms of finance for the early adopters, then yes, it will be through the normal channels for those guys.
Next one is a very important one, and I think there's some misunderstandings. I think it's going to be, I'm seeing a very good answer coming from you for sure. Can you compete with the engine manufacturers like Rolls-Royce, Safran, Lycoming, etc., which have millions of hours operating in terms of safety?
Yes, absolutely. So as I explained earlier, the benefit that we've got is the decades of experience of what to do and what not to do with these engines. We're not developing an engine from scratch with the very low technology baseline that the early pioneers had to work with. We've got all of the combined knowledge of the industry for designing, building, manufacturing and operating these engines for decades. That's our starting point. And then on top of that, our team is built up of people that have worked in many of these companies over the years and have got very wide experience of best practice and where the bar and the level and what the typical processes are to be able to guarantee the levels of safety that you need. On top of that, we're working to the very latest amendments of the certification standards, and the level of engineering technology, both in terms of simulation, manufacturing and testing that's available today, is just at a totally different level to what was available in the 50s, 60s, 70s and 80s when the engines that we're flying around in today were designed and developed. So you can't expect the engine to work perfectly out of straight out of the design. You know, you have to put it on the test bench. You'll end up breaking lots of things and modifying lots of things, and then we've got to drag ourselves up bit by bit, building confidence and experience in the capability of each of the components and the subsystems until we've demonstrated that our conforming prototype can deliver everything that it's supposed to do as per the operating handbook, and that we've qualified it for the number of hours that it's going to see in service. And once we've done that, it is airworthy. Yeah, that's an international definition. It's the same rules for everybody. When we've done all of that work, it is airworthy. And what I would say is the unique advantage that we have is because we manufacture everything ourselves, we have total control over quality. We can choose to go the extra mile with inspections, with manufacturing tolerances, with the time taken to assemble these things, because it's not a big cost driver for us. We make our margin on the end product, not the individual pieces. So we're going to town on everything that you could possibly do to make this the best little engine that it could ever possibly be right now in 2025. So yes, absolutely, I think we can deliver an airworthy engine that's going to be reliable and safe in service. It's going to take me a while to put 1 million hours on the thing, or 10 million hours, or 100 million hours, right? That's a lifetime's work. So I can't compete with that today, but you don't need to compete with that to be airworthy. If you go and read the certification standards, they tell you exactly what you've got to do to be airworthy, and it doesn't ask for 10 million hours.
I don't know, Jason,
Fantastic
you
point.
underestimate Ruben and I. We do fly a lot, and that leads to one of the following questions in the next little bit here. But I think that's good. Tim's asking a really important question that says, what are the biggest remaining unknowns?
The unknown unknowns. So we're in a great position now where the aircraft, the engine, the manufacturing infrastructure, the team, it's all sufficiently mature that we can see what we've got to do to get this thing over the line and into production. But it's the little nuanced things that come out of testing that are the things that you have to react to and be responsive. The starter generator has been a really interesting learning curve for us, because all the stuff that we thought was going to be difficult wasn't. And then some of the things that we didn't think were going to be difficult have really made us scratch our heads a little bit and required a 2, 3, 4, 5 design iterations. And we're only talking about changing things you wouldn't even notice, but they're the difference between things working or not working. And it's that kind of thing that you've got to churn through until you've got all your ducks in a row and it works properly. So I laugh about it, so I joke about it, but it's genuinely the unknown unknowns. It's the things that are going to crop up in testing that we've just got to respond to and resolve. And they're not threatening, they're not going to stop us, but you can't put your finger on it and say, I've got this list of tests to do, and once I've done all of those things on the day I say I'm going to do, everything's going to work, because it doesn't work like that. Your test equipment might not work, your sensors might not work. When you've got that to work, you test your equipment and it just doesn't behave the way you thought it was going to, and then you have to respond. So it's just dealing with those realities, but you've got to remember that's why the barrier to entry into these markets is so high, and that's why we've been so stifled of competition, because there is a lot to do and it is difficult, but you just work through them one by one, and the laws of physics can't fight back. Once you do the right thing, it just works. It has no say in the matter. Do the right thing and it works, and that's what we're doing.
Fantastic. Can you imagine if you depended on the supply chain to do this? It would be impossible.
Yeah.
Back and forth, all these iterations you talk about, and vertical integration is the only way and proving that. Fantastic.
I'm
Next
dying,
one from Lee.
I'm dying to tell you a story about bearings, right? And I can't tell you, I can't do it publicly, but I'll tell you afterwards. Yeah.
Next dinner. All
Yeah.
right. So Lee, do you need suppliers from the US side?
Do we need suppliers? No. No,
You don't have suppliers. You buy
no.
material, right? You buy raw material, right?
There's a couple of bits and pieces that we buy at the moment, but it's our stated strategy to purely buy raw materials. So we try and source as much as we can locally.
Well, you don't buy the screens. You buy the wires. You don't buy the hardware targets for the avionics. But that's pretty much it, right? The rest you get in the house.
Yeah, we do buy those things. Yeah, we don't make them.
You buy those.
Yeah, we buy wire, we buy connectors, we buy the screens. We don't make microchips, we don't make LEDs, things like that. But those are things where they're commodity things where the broader market sets the price. The things that you have to make yourself are the things where it's got an aerospace stamp on it, so people know where it goes, because that's where you get the factor of 30 multiple on the price versus what it costs to make. Those are the things that we've got to control to be able to deliver a helicopter that people can afford.
Yeah,
That's called the Hill
Exactly.
advantage. Nobody else has. Yes.
exactly. Next question is coming from Matt, and I'll answer the first half. Jason, you can answer the second half. It says, will we see Misha and Ruben on their world trip in an HX50? And will Jason have time to come and join them? So yes, you'll definitely see Ruben and Misha. We're actually going to be having 3 helicopters so that we can showcase it in the right way and show everybody the incredible world that we have to explore, but also the helicopters that we're going to be flying. And so we're really looking forward to that trip. That's going to be coming basically right after production starts. So we're really excited about that. And then I don't know, Jason, you're going to have to answer the second part for us.
Yeah, I'm obviously not going to be able to do a whole world tour because I've got a factory to run and lots of helicopters to make now. But I'm definitely going to come and join you on some of the legs. And whether you want me or not, I'll know where you are because I'll be tracking you. So yeah, I'll come and join you on some of the legs. I'd like to do some flying in the US. We're going to go and do some flying down in Australia, and Europe's pretty easy for us from here. So yeah, we'll come and join you for some legs.
Looking forward to that.
Fantastic. That's a promise there, Misha. So it's
Yeah,
done.
I'm looking
It's
forward to it.
guaranteed. All right. Harvey is asking about TCAS and ACAS systems combined with synthetic vision, where there'll be that system and also multi-spectral camera HUD system that allows you to fly in extreme fog conditions. So can you talk about those 3 things?
So let's do that.
Multi-spectral camera.
So let's do this in order. In terms of TCAS and traffic awareness, as we demonstrated on the Digi Cockpit, you've currently got ADS-B traffic built in. That's our chosen traffic area, solution. We can also the unit that sits behind that can also have the FLARM input as well, so we can pick up the stuff that the gliders use, which is interesting for lots of helicopter pilots because we're low and we're around where gliders are. So ADS-B plus FLARM will be readily deliverable. There isn't any plans to do any more sophisticated traffic systems at the moment because they're very expensive. And I think this whole area is going to change dramatically over the next few years as new types of aircraft come into service and the airspace gets upgraded. So I think we will just follow where the market goes with that and deliver the most appropriate solution. So traffic is in there as standard with ADS-B in. It's natively displayed on the Digi Cockpit. So yes, we do all of that. What was the next one? Traffic is the first one.
Heads-up display.
Yeah. Heads-up display. So there isn't a plan at the moment for a head-up display. I've said before that we're looking at all sorts of things in terms of augmented reality and different technologies that are coming forward with mixed reality glasses and goggles and things, but I don't think the technology's there yet. So we've been presented options where you can project all sorts of things onto the entire bubble. But again, they're expensive, and how much do they really add to a VFR helicopter? So that's probably not something that we'll do. In terms of the multispectral cameras, we've already shown that we're using a normal visible light camera to supplement your field of view in very steep approaches on the background of the Digi Cockpit, and we've found that works really nicely. It's not a substitute for looking out the window. It's not an excuse to have an excessively big instrument panel, but it aids to minimize the blockage that's inherent in any panel in any helicopter. And then using that same approach, we've also showcased an IR-based night vision camera that works really, really nicely. That's hugely powerful at night, and that will be an option subject to regulatory approval for the night flying machine as well. So we'll definitely do those 2 things. Your traffic's ADS-B, and I don't expect to do a head-up display.
Okay. Noel is asking, is there going to be able to, is the HC50 going to be able to carry a stretcher? Because I know at least one customer who needs it. Hopefully the customer doesn't personally need it, but yeah.
It's not a duty that we've actively explored properly yet. So it's been asked before, and we've considered options of looking at different door solutions on one side of the aircraft, but we've done nothing with that at the moment. So if there's a significant market for it, then we'll look for it. I'd have to say at the moment, I don't think the door arrangement would support the conventional Jet Ranger style loading, where you come in from the one side and sit it where the pilot seat is. I think it will be too difficult to get one in there for our platform at the moment. But it's something we could look at. It's something we could look at a different solution for the B pillar and just stiffen the door frame. So I'm open to it. It's not being worked on actively at the moment.
Gary Arnold is asking the following question. Why is the radio talk button not in the usual place on the Cyclic? Or am I mistaken?
No, you're not mistaken. You are absolutely correct, and it depends what you define as usual. If you take an S-76 or some of the bigger helicopters, it's quite normal with aircraft that are designed to have a 4-axis autopilot that you've got a trigger that's force trim release on both flight controls, in which case you put the push to talk button somewhere else. So the main difference here is most light helicopters that you're used to were designed before autopilot systems were available to aircraft of that size. So it made sense to use the trigger position for the thing you were using most of the time. In our case, we have a force trim release button, or it's your primary input into the autopilot system that you're going to be tapping away on regularly. And if you've got a force trim release as a trigger on the Collective, it would be quite counterintuitive to not have that in the same place on the Cyclic. So we've elected to simplify and unify the way the sticks work. So your force trim release on Cyclic and Collective is both the trigger, which then means you've got to put the radio button somewhere else, and the next most obvious place to put it is a big thumb pad right in front of you. And that's no different to a lot of the early 22s and 44s, where it was just a button on the Cyclic head before the pistol grip arrived. So this isn't unusual. It isn't something that hasn't been done before. The key driver is every single HX50 that will ever be produced has stability augmentation and an autopilot. It's part of the essence of how the machine flies, and so the flight controls have to reflect that.
Great. Harvey is asking a question. Would you be open to selling your engine and gearboxes to third-party aircraft manufacturers and private experimental amateur builders?
No, the engine is very much our crown jewels, and we have big plans for what we're going to put that in ourselves. So what we're trying to do is to facilitate a new age in general aviation. HX50 is the first part of that, but it all comes from being able to make cost-effective propulsion systems. So we'll be keeping that for ourselves to create lots of exciting things for you in the future.
Right, Jane Page, next question from him. Is there going to be a blade holding arm on the tail for the folding blade option?
Yes. There is. It's underneath the tail cover, so the tail cover that you can see on the top of the tail, you open that and there's a location in there to support the blades.
Okay. And Julian is asking, why did you choose to reverse the traditional cockpit layout in the digital display, placing an altitude on the left side and airspeed on the top, rather than conventional airspeed left, altitude right? Have you considered the potential impact this might have on pilot confusion, slips, or errors during flight?
I think that traditional layout is very true in fixed-wing aircraft, but less so in helicopters, which can have gauges all over the place. And so what we set out to do was design something that was as simple and as clear as it could possibly be. And so we've just really started from first principles. And remember, this is a VFR helicopter. You know, you should be looking out the window, and it's it's a different level of instrument scan required for instrument flying to what you need for a VFR helicopter. So we've just tried to design the DigiCockpit to be as simple and as clear as we possibly can. And we've tried to logically group the gauges. So your power and your RPM gauges and your fuel gauges and your engine gauges are all grouped on the right-hand side. And then your altitude and your vertical speed, which are of course related. And then the stability functions are all grouped on the left-hand side with your primary attitude control in the center. So it's really just about using the space as efficiently as we can to have big, clear dials with needles so that you can gauge rate, state, and limitations as well as the values. And we just tried to do the best job of that we could.
Right.
Right. From Tordar, he's asking, I just watched a video on a Sling TSI build on the Aviation 101 YouTube channel. They mentioned a separate push-to-talk button on the instrument panel, in addition to the PTT on the stick. What are your thoughts on that?
Again, there's a big difference between flying a helicopter and flying an aeroplane. And we kind of offset that because we have stability augmentation. But in a conventional helicopter, your hands are always on the flight controls. And so you've never got free hands wandering around to press things on the instrument panel. So I don't really see the advantage for that. I mean, for doors off operations, it's quite normal to have separate push-to-talk buttons on the seats for the passengers or floor switches for passengers. And we'll make adequate provision for that. But for the pilot, I don't see any advantage to it. You'd always use the one on the cyclic.
Yeah, on commercial operations, I know that obviously you're not going to have dual controls in when you're doing a commercial operation, whether it's with forestry workers or whatever happens to be. And so typically on a lot of commercial machines, they'll have the switch on the dash or in some place that the passengers would be able to access it. But yeah, that makes total sense. So Phil's asking the next question, and it says, do you see that the recent FAA finalization of the Mosaic rule positionally impacts HX50 use in the US under its experimental class?
So I've been following Mosaic, but I haven't looked at the final rulemaking yet. I've been very much focused on our engine. So I've spotted the question that you've posted on the app, and I'll respond to it properly. But I want to go and just look at the final documents before I make any public comment.
All right, we're getting to the end of it. We have been already, a little bit over an hour. And we're going to have a couple more questions, and then we're going to wrap it up. Next one is from Samuel. He's saying, living in a waterfront property, is there any being able to fit floats on the wheels or a skid to make it a marine version?
So there's obviously emergency floats, which are provisioned for. We haven't considered fixed floats, but there's no reason why we couldn't do a fixed float skidded version. It would obviously impact the cruise speed, but if the utility outweighed the advantage of some knots, then yeah, there's no reason why we couldn't do that. The skidded version would make that very straightforward.
Okay. And yeah, Edmund is asking, has Hill considered making a turboprop GT50 variant?
I couldn't possibly comment. But yes.
I love this. But yes. Fantastic.
All right. Will Hill Heli be offering a ferry flight option for U.S. customers as an alternative to shipping the containers?
So we won't offer that directly, but there will be many people within the community that are more than happy to facilitate that. So it will be an option for people, but it's not something that will come directly from us.
Yeah, and it's something that people need to understand, that it is very weather dependent and very seasonal dependent. You have a lot of bad weather that happens in between, from going from the UK side over to the US side. And so it has to be really carefully done and done at the right time of the year. So, And just going back to Harvey's question, he kind of posted another one, just correcting what his actual question was. It says, I wasn't referring to traffic, I was referring to terrain collision avoidance systems.
The synthetic vision, right. Okay, so people have asked us for synthetic vision, and we are looking at synthetic vision, and that transparent layer that we have behind the DigiCockpit is there to enable a source of synthetic vision data to be piped into the DigiCockpit. The problem that I have with it at the moment is it isn't very good from a helicopter point of view. So the synthetic vision databases are generally designed for aeroplanes that are trying to avoid mountains in IFR conditions. Well, helicopter pilots that fly down and in amongst all of that stuff, that terrain, if you were to ever try and use it for that purpose in poorer weather, the resolution of that data has to be so much better than is necessary for an aeroplane just trying to avoid a mountain or an obstacle, that you could argue that it would encourage people to fly in conditions that are not suitable for VFR helicopters. So we're playing that quite safely at the moment. We're looking at different sources of data and we're looking at different implementations, but we haven't got one yet.
All right, so we had an incredible session, a little bit over 2 hours, many questions. What an update, Jason. It was an incredible update. And to end, we're going to be also giving you the opportunity to consider attending one of our presentations that we do daily. Misha and I, we have an informative presentation that we do every single weekday, and we'll be very happy if you can attend one of the upcoming ones. It's worth it. It's about 30 minutes, and we go over every single detail of the aircraft and also the opportunity to pre-order the aircraft under special conditions, which is still available, and it's ending. It's fading away as we get closer and closer to production, as we all have been witnessing, and now with this update, even closer. So make plans to attend one of the upcoming ones. Special pricing is still available, and this pricing is fading away. At the end, Jason, I have a personal question, and I think it's an important one because many people have asked, and that will give you the opportunity also to close, and we'll be announcing the next AMA soon. So great to have everybody, thousands of connections today from literally all over the world. Jason, the question I have is that people ask, where are you standing with the CAA? What has been the experience with the regulator? How do you see it rolling? And what has been the interactions with the regulator? Because some people think that this is something only going to be happening when everything is ready for delivery, and we knock at the door and say, hey, we have it ready. Can you come and inspect for the permit to fly and then certification? Can you give us a good overview of that, where it is standing, and then we can close it and we'll be in this session.
Do you know what the last slide of this presentation was that we recorded and then took out because the presentation was too long? It was all about what we've been doing with the CAA. So the CAA have actually been instrumental in every stage of developing what HX50 is today. So I sort of worked with Alan Carter, the head of the GA unit at the CAA, from as early as 2016, 2017, to come up with the regulatory sort of approach that we were taking to fuse latest certification standards with the amateur build regulations to enable us to create a new innovative aircraft. And Alan and his team have supported us at every single step of the journey. Now, while we were basically working out how to make this helicopter, how to make the helicopter, how to make the engine, and how to build the factories and doing all of that practical stuff, we haven't lived in their pocket the whole time there, because it's a waste of their time, because we're not ready to come back to them with an educated ask of, right, we're ready, let's go through the approvals process. But over the course of, I would say, the last year in particular, we've really been ramping up that activity, and we're really starting to push through the organizational approvals now for the design approval that we need to carry as an organization, the production approval that needs to be in place for us to start production, and then crucially the UK permit to fly for the engine and the aircraft, and then the full type certification for the engine and the aircraft. And hand on heart, you could not have asked for a more supportive, proactive regulatory partner than what we've got with the UK CAA. I think the timing has been very fortuitous for us, with the CAA getting their powers back from Europe just as we were about ready. And I think the landscape of what developments are going on in aviation at the moment also plays very much into our favour, because we're seen as a safe bet for the regulator's time, somebody that's going to get there and get there in short order. So we're being wonderfully supported. The team are fantastic. At the moment, we have a different round of specialists here every month to work through each of the subsystems of the aircraft, and then we're actively building relationships between our specialists and each of the specialists at the CAA for the initial approval of the X model to start with, and that will rapidly then blend into the full type certification for the C. So we're in a very, very good position with the CAA, and they have been wonderful. I think the response you get out of any aviation regulator depends very much on how qualified you are, and whether they deem you to be somebody that's worthy of the very limited resources that they've got. So it's quite clear what we're doing and where we're going, and it's recognised by the regulator, and so we're getting all the support we could ever ask for, and we've got a really healthy relationship. Like I say, we got a mixture of huge support from Chris, the test pilot, the other day on what could have been a very contentious area with the DigiCockpit, because it is different. And he was also more than happy to push back and say, no, I don't like that. Let's have a careful look at that. And so that's what the approvals and the sanity checks that come from that process are supposed to do. So it's working great. It's happening right now, and they are pushing us. They're saying, come on, we want more, do more. It's not the other way around. It's not they're running into the ground and they don't have time for us. They're saying, come on, if you want to hit your own timelines, you need to talk to us now. And so you really couldn't ask for any more out of them. So they're great.
Fantastic.
I honestly don't think that's going to be a major problem. It's not going to be the CAA that hold this up.
Fantastic. Very good. So everybody attended today, thank you very much for your time. I think it was a wonderful time spent. For the ones who have not attended, remember you can go to Hill Helicopters website and register for one of the upcoming daily presentations. For the ones that have attended and have received an offer, that offer, as you know, is expiring. If you want to have the best pricing available, do it now if you made that decision. And for every single client that has supported this program, thank you very much. And obviously, it's an extended gratitude from Jason that has been enabling this incredible, disrupting program that is coming back and giving that life to general aviation. Thank you very much. Have a great morning, afternoon, evening, wherever you are in the world.
Thanks a lot, guys.
Next time.
Thanks for your time, thanks for your questions, and thanks more than anything for your support.